Today I'm basically going to be talking a bit about. So I'm sort of like considering that people have little to like no knowledge of what machine learning is. So just like picking up from where machine learning started off, what it exactly is, to sort of like trying to figure out how does machine learning exactly work, what are the objectives of actually doing machine learning or using machine learning for any sort of a task. And then we'll sort of try to discuss where it sort of transitioned from traditional classifiers to how these big chat GPT type models are sort of working and what they're doing so differently that they're able to produce such good results. Right. So a brief introduction about myself. I'm Anubhav. I'm currently a PhD student at NYU. And yes, I basically joined STEMaway, I think, 3 years back. And we had basically been where you were. But yeah, I had a great experience with STEMaway. So now I'm basically trying to give back in my way. But moving on. What so just like trying to define what machine learning is, what a traditional program would in general do is that it takes in some data, it takes in a program, and it gives an output. Because the program in this case is pretty much well defined, and it's defined to the extent that it's a simple function that has some data and it has some defined output that it would produce. But what machine learning, in fact, tries to do is that it tries to learn this program itself. So what it wants to do is that, there's some type of data that you have, and you know what the output you would expect from this data for any particular task. And now what you want to basically do is you want to learn this program or this function. If I were to sort of like, just like mathematically, just bear with me a bit. If I were to mathematically understand this, I would say that I want to use for some given input X, I want to learn a function F and produce an output Y. So what I'm basically trying to do is I'm trying to learn a function Fx. And this I'm trying to do using machine learning without giving no explicit information whatsoever. So I want the machine itself to learn this function based on some past experience that it gets from the data. Right. So why do we use machine learning? So this is like a very, very popular example. And this is probably one of the first few use cases that people build using machine learning. And this was definitely one of the first few that I had built using an Andrew NG course. So it's popularly referred to as an MNIST dataset, and it's basically used for detection of handwritten numbers. And the task is basically you want to look at these handwritten numbers and you want to basically say what the number actually is. So now in this case, the input would be the image of the handwritten number, and the output would be the label associated with it, which is the actual true handwritten number. And you're trying to, again, learn this function, which basically does this classification. You have numbers from 0 to 9, and you're basically learning this function to do this 10 class classification. So what are some other sort of use cases where ML is used? So it can be used for like, especially I'm going to focus just like a bit more on the vision side because I come from a computer vision background primarily, but it can be used for like various tasks such as facial identity or facial expression detection. It can be used for handwritten words, as we saw in the previous example. It can be used for spoken words, which uses speech data and then uses similar classification models. It can be used for medical data. A lot of applications are coming up where you want to detect tumors just by using machine learning, and these have shown almost human level performance now. It can be used for generating patterns. So a lot of these, in fact, even ChatGPT is a generative model in itself. So what it basically does is that you could give any sort of random textual input. It could be also controlled by random sort of a vector. And what you want to produce is a realistic looking image or a realistic looking text paragraph, and so on and so forth. And Yeah, sort of like the applications go on where it can be used for detecting credit card transactions. You want to detect anomalies there. You want to detect anomalies in other sort of applications such as nuclear power plants. It can also be used for detecting, it can also be used for predictions, which are going towards more towards regression models, which we will talk about. But yes, coming back to how we define machine learning. So Herbert Simon, who was again one of the early people in this field, he sort of defined machine learning as any process by which a system improves performance from experience. And they sort of say that, so this is a very broad definition, and it incorporates some other learning sort of paradigms, which we won't be discussing as much in detail, but in general, you want to improve the performance of an algorithm uh, based on some given metric. This metric could be accuracy, this metric could be something else in terms of when you want to do data generation or image generation. This could be a metric based on the quality of the image. But essentially, you want to improve the performance on any given task T with some experience E. And this experience is what we call the training data, or whatever past data or past experience that the model has seen till now. And this sort of a learning task is defined together with this performance task and the experience. Right. So let's try to define a learning task. I know I put in all the answers there as well, but let's start with like the simple example of recognizing handwritten words. How would you try to define this in terms of what is the experience here? What is the performance be here? So so the performance, what we are discussing over here, is accuracy performance of the words that get correctly classified by a model. And the experience that we're using over here is a database, pre-existing database that was already collected, which contains human-labeled images of the handwritten words. Similarly, a lot with sort of autonomous driving. So you have tasks such as driving on a 4-lane highway using vision sensors. So how would you judge the performance of a model that can do this very well? You would say that it does well based on how long it can go without actually making error. And similarly, you would give it some past experience, which is like a sequence of images, steering commands, etc. that is constantly being recorded by most modern autonomous vehicles. And similarly, you can have tasks such as categorizing emails or spam. And again, you would judge it based on how well you do the classification task. And a classification task is generally judged based on the accuracy performance. And to train such a model, you would give it a database containing a lot of emails with some given human annotated labels. So generally, we define learning in different you can do learning in different ways, and this generally depends on the type of data that you have for this learning task. There are more and more sort of learning paradigms which are coming up constantly, but these are some of the more popular ones. So you have supervised learning, which is the traditional learning algorithm where you already have a labeled data set, which contains some sort of some number of data points with some number of features. It also contains labels for each of the data point, and you are basically focused on learning the function f to learn from this particular data set. And then you have unsupervised learning, which is more of a way in which you want to learn patterns in the data. So this sort of a data set generally does not contain an output label. So it contains data points with particular number of with each data point basically containing a particular number of features. But you want to categorize these features together, or club them together, learn certain attributes in which you can club certain data points together. But such unsupervised learning algorithms do not contain any human labeled output. And then you have semi-supervised learning, which is a combination of supervised and unsupervised, where you have few labeled data sets, few labeled data points, and you have a vast number of unlabeled data. And then you have reinforcement learning, which is more of how you take an action based on a past experience. And it's basically works in a reward and action sort of a paradigm. But we'll discuss more about each and every one of these later on. And the self-supervised learning is basically you have training data without the desired outputs, but this learning sort of algorithm can generate its own pseudo labels, and it can do a learning process using these pseudo labels. So a very simple sort of a supervised learning problem is regression. So how we are talking about predicting the stock, how it sort of changes in the future. We can do that based on some past experience, which is how the stock has performed over the past couple of months, couple of years, a couple of days even. And what sort of a data set would you use for this? You basically would have an XY data set where the X is basically what the stock price was at any given point of time. And the Y label is basically, the Y label is the stock price at any given time, and X is basically what sort of features you have collected off the stock. And what you want to basically do is given at any given new time, which you want to predict what the stock price would be, given these same set of features. What a classification task does is it gives categorical output, so it doesn't do like a real valued output prediction. So let's say you're given again a data set X and Y, and X is basically your features representing. Let's take a simple classification task. Let's say you want to do a classification between dogs and cats. So your X over here is basically the image of dogs and cats, and Y is your categorical label, which can be represented as a binary 0 or 1, 0 representing dogs, for example, and 1 representing cats. And you basically feed this into the machine learning system, and it basically gives you a prediction based on whatever data you've sort of given it. Right, so let's take a quick example. So I have 3 supervised classification tasks over here. So the task over here is basically classification between the blue dots and the yellow dots. And you learn a decision boundary, which is represented by this black line in the middle. Which of these classifiers do you, looking at this sort of depiction, think is the ideal case that you want to get to? Or which one is like the best classifier amongst these? So, does anyone want to answer? Take a shot.
Anupam, there are some answers in the chat.
Oh, okay.
Akbar is saying the third, and Brian saying middle, Raghav second. So that's middle again. So 2 for the middle and 1 for the third.
Right. So the correct answer is, in fact, the middle one. And so what you want to be looking at when you're you're also going to be building classifiers. So the first one, at least, if you look at this, it's very specifically fit the training data. What that means is that it's overfitting on the training data. What could basically happen in cases where the training data could be noisy to some extent, where the training data might have some anomalies. If you try to exactly fit the training data completely, you might lose out on the generalizable capability of your machine learning model. So it would correctly classify your training data with approximately 100% accuracy. But this model might not be generalizable to some unseen data. So what you want your model to be able to do is that it shouldn't just learn this training data completely, but it should learn features of this training data, which can be applied to other sort of similar data. And the second one is like a perfect classifier in which it learns somewhat of a middle ground between having high training accuracy and also being generalizable. The last one is an under-fitted sort of function where it's doing badly on both the training data and it will do badly on the testing data as well.
So one question.
Right.
Between the second and the third, you said that the third is doing badly, which visually we can see, but how do you define badly?
So it's generally like based on like some metric of classification. So it can be like an accuracy. So what you generally do is when you sort of want to do a training paradigm, you split your training data into a training set and a validation set, and you see the accuracy performance split between the training and this validation set. So if it's sort of like comparable, you know that you're learning generalizable features, but if there's a big drastic difference where your training accuracy is extremely high versus your validation accuracy is extremely low, you know that you've overfitted on your training data. And similarly, the last case is where both the training accuracy and the validation accuracy are extremely low, which means that you haven't been able to even learn the training data well.
I see.
Right. So let's take a problem which is going to be quite relevant for all of you as well. So let's take a text classification problem. So talking about like some particular use cases of a simple text classification problem, you could again do as something as simple as the email spam versus non-spam classification. But what I want to get at now is that text is basically words, and it's a sequence of words. And this sequence of words is something that the computer absolutely doesn't understand at all. So computers basically, it works in like binary, it works on zeros and ones. What is this representation of this? Just like appending some particular alphabets together, this doesn't mean anything to the computer at all. This has no significance. So how would you sort of go about making the computer understand this sequence of words and also a sequence of different words appended together? Does anyone sort of have any thoughts? Let's talk about something that would be extremely naive in this case. What's like sort of like the simplest way in which you would want your computer to basically be able to look at two different sequences of words and say that, hey, these look similar enough to me for me to say that these can be classified together, or these are so distinct that there's absolutely no comparison and they could be saying absolutely completely different things.
Anubhav, there are some answers again in
Okay.
the chat. It's speaking in code to it.
Okay. Could you elaborate on what you mean by that?
Feel free to unmute yourself or just type again that either it works. It feels like it's along the correct lines. All right, why don't you go ahead, Anubhav?
Right. So let's talk about like the easiest way in which you would do that. And this is probably, I'm not sure, but this is probably one of the first few algorithms that came up. So you want each word to be represented by some numeric value. So one of the easiest ways, you create like a hash table where you say this particular word is assigned a number 1, this particular word is assigned number 2, this particular word is assigned number 3, and so on and so forth. So now, at least in a very simple way, you have represented all the words in the English language into numerical values. And numerical values is something that computers can work with, or it can learn a function based on these numerical values. Now, let's try to, so what sort of a problem would come up with such a learning algorithm is that you have millions of billions of words in the English language. And once you have represented each with a particular numerical value, there's going to be one word which is sort of like 1 billion something. So people said that it's possible that my current classification task absolutely does not make use of all of these words in the English language. So now an easier way is to only look at the words that come in your training data. And you can basically say that words you haven't seen in your training data to be some unknown character. And it can just be represented by some extra, let's call it like a -1 over here. So the simple sort of approach is like a bag of words approach, which would basically count the number of times a particular word has appeared in your given training data for each of the let's say for a binary classification problem for each of the 2 classes, and then it would do a comparison for any new given data point that comes up in your testing set, do a comparison of how well it matches with both of these given bags. But there are again issues with such learning algorithms as well. And the issues, I don't know if you see it immediately, but the issue would be they're binding words which come way more often, and they're binding words which would influence the accuracy of your particular model a lot more than a normal word, than you would normally like them to. So the primary words that should influence are very specific terms that may not appear as frequently in your training data set, but they are the ones that sort of assign it as spam but not spam. So you might only get the term, let's say for an email classification problem, you might only get the term lottery or a $5,000 cash reward just once mentioned in a 20-line email. But that's sort of like the primary term that you want your model to be focusing on. So a bag of words completely loses the sense of which part of this is more important, because it's just giving equal importance to everything. So then people sort of like came up with TF-IDF factorization, where they basically said you can inversely give the importance based on how frequently it comes up. So what this basically means is that binding words or like common words are basically given lesser importance, while the rest of the words are given a bit more importance. And this was a significant improvement over traditional bag of words based classifier. And so you basically do a TF-IDF based vectorization where each sort of word is given some sort of a vector representation. And then you can use like some sort of classifier based on this. That's where the next point comes in, is like, how would you learn from this representation? How you've sort of, in some very simple sort of methods, you've gotten a vector representation for each word. And then now, because you have gotten a vector representation, you can use any sort of classification model, be it, I haven't talked about these classification models, but be it any sort of support vector machine, be it a logistic regression, but you can feed this sort of a vector representation to any given classifier, and it can learn something meaningful out of this. So coming to what self-supervised learning did, and this is like moving forward from like traditional ones to going more deeper into what ChatGPT does, is that now you have this. Now the problem with sort of supervised learning was that you require labeled data for your learning process, and what the biggest limitation of sort of this approach is that you require humans to actually sit down and annotate a large amount of data. And this is extremely time inefficient. It's also cost inefficient. And it's absolutely not possible for a large number of applications. So people sort of came up with self-supervised learning, which was that my data itself, it's any given data scraped from the internet. I will generate pseudo labels for the data within itself. And I want the model to basically learn the basic intuition of what language is or what the English language is. I want my model to be able to understand what the English language in general, without giving any specific task, what it sort of incorporates, what are the different styles in which you can write the language, what is the correct way of forming a correct sentence, and so on and so forth. So to define self-supervised learning is a machine learning process where the model trains itself to learn one part of the input from another part of the input. So what this sort of means is that you hide some, at least in like the most standard way of self-supervised learning, you hide some part of the input and you try to predict that hidden part of the input from the rest of the input that's being fed into the model. So it predicts like some future value based on like some past that it's seen. So this is basically where the GPT basically, or a transformer model, and what they're sort of doing so differently comes in. So what they're doing differently is that they're basically using self-supervised learning, and they're using a vast amount of data. And they can do this because they don't require annotated data for training. So they can absolutely make use of any data on the internet. So they're models that basically scrape all Wikipedia pages, everything that's basically online, and they're training their models on trillions and trillions of data points. And what does this model learn? It basically learns a representation of the English language in general. So it would learn how every sentence is sort of framed. It would learn, if this is the first few words of the sentence, how can I complete the sentence to mean something, to be something meaningful? So, and this is sort of like a task. This is sort of like a unspecific or a general pre-training task. So it's called like a pre-training model. So it takes a data set with like no labels, it learns a pre-training model on some pretext task, and then it applies this learned representation. It can apply it to any downstream task using some transfer of knowledge from this large corpus of data. So and what traditional learning algorithms used to do, and especially with deep learning, which is also very data intensive, was that it always used labeled data. And that sort of was a big limiting factor. So what are some sort of examples of these pre-training tasks? So the most common one that this sort of field began with was a masked language modeling. What it basically means is that you mask out a particular word in your sentence, and you ask the model to predict what that masked word is. So let's take an example. So if you look at the example below, I know this is an example for next sentence prediction, but let's just take the sentence from the CLS token to the SEP token. So the sentence basically says, the man went to mask store. And what would you give the task to your model to be? So you would basically say, predict this masked value. And because you already have the exact sentence, or you know the exact sentence that was already there in your training data, you can already assign it a label, which might be something like the man went to the store. And then you can check for correctness, and you can find, or you can train the model based on what the actual sort of value that is. So similarly, you have different tasks such as next sentence prediction, where you give one full sentence or a set of sentences, and you ask the model to predict the next sentence. And you already know the next sentence because that's sort of already present in your large corpus of training data. And similarly, you have other tasks such as a translation language model, where you already know the translation between two languages. It could be like English to French. You already know like the English language, and you basically ask the model to predict the French version of the same text. And similarly, you have permuted language modeling, where you give a permutation of a particular sentence and you ask the language model to unpermute or to find the correct permutation of that particular sentence. Right. So just to like summarize this, so these were sort of like ways in which these large GPT sort of models are making use of this large amount of data to pre-train the model to learn the general language. And then they basically fine-tune it using some labeled data sets on like very specific tasks. This could be as simple as an email classification task, because it's already learned the English language so well, it can exactly understand what some particular email is trying to say. Now coming to like unsupervised learning. So unsupervised learning is basically you have some training data, you don't have any labels assigned to those training data, you just have some representation of some let's say you would, again, let's go back to the original example. Let's say you want to do cats versus dog classification, but you're given some training data with no labels. How would you do this? So each example is sort of represented by a feature vector. In this case, you might want your feature vector to be something a bit different than giving the exact image, because a learning algorithm with absolutely no prior, with sort of like no label can probably not learn to distinguish between just like two images. So let's say you give like some set of features for like each cat or dog to be, let's say, like the height of the animal, the weight of the animal, and you want your model to be able to classify just like using these two attributes. So your model with like some certainty might still be able to club them together based on like the height and weight ratio of a dog versus height and ratio of a cat, which can be distinct enough for it to be able to, with some accuracy, learn like two different clusters. So the primary aim is sort of to find patterns of similarity to club data samples together. And I also wanted to like sort of like very briefly like touch upon what recommendation systems are, since we are going to be talking about this a lot later during your internship. So there are different types of recommendation systems. So recommendation systems in general can broadly be encapsulated as saying that given a user's past history or given some amount of past experience, you want to give the user a new recommendation for what the user may or what the user may like to view in the future. So taking a very simple example of, let's say, Netflix, a basic collaborative filtering based recommendation system, what it does basically is that it looks at how users in general perceive choices. So how one particular user, let's say one particular user likes to watch the first two movies, and you know that another user also likes those similar two movies, and the first user has watched a new movie. So with some certainty, you can say that because these two users in the past have had similar choices, you would you can say that in the future as well, they might have similar choices. So you would recommend a movie that the first person watches to the new user. So again, recommendation systems are also like completely unlabeled. You don't have any true label of true labels associated with all of your training data. And similarly, you have content-based filtering approaches for recommendation systems. So basically, the types of movies that a particular user has watched in the past, what are some sort of like, where can you sort of like, or how well can you predict the user's preferences to some new movies based on, let's say, some particular genres or like some particular cast of these particular movies, and predict what the user would like in the future based on its past preferences. And in general, most recommendation systems these days use like a combination of both content and collaborative based filtering. And then you also have context-based filtering, where you also take into consideration other sort of context about where is the user present, which locality, what sort of devices the user using, what's the time zone that the user is in. So the user's preferences could drastically change based on like what time of the day the user is viewing Netflix, and so on and so forth. So just to like coming to like trying to summarize this and giving some advice for how in general machine learning sort of works in practice. So machine learning sort of works in like 5 different stages. So you start with like understanding the domain, you look at like what prior knowledge and what are the goals. And then you do some data collection, data integration, you do some cleaning, you do some pre-processing of the data, you learn some model, you get some results based on the model, you interpret the results, you draw some conclusions based on these results, and based on like whatever discovered knowledge that you have, you again go back in loop and you again do the same process again to get better results based on what you're learning from the past sort of world. And this is like a ongoing loop where you do this repeatedly for like doing different models, and you sort of want to learn what's this particular model failing? What was I doing wrong in this sort of scenario? What can I do differently now? Where was it like some pre-processing step that I wasn't doing correctly? Was it not the right model for this particular data? Was it just that this particular data cannot be used for this particular task? So this is just like, again, so like on similar lines, it's like some personal advice on building ML algorithms. So this is just like something that I in general personally follow whenever I start a new project. So whenever you start, it's very important to like completely and very accurately understand what your data is. Because at the end of the day, your machine learning, what you want to do is make your machine learning model understand that data. So if you don't understand that data, you cannot make your machine learning model understand the data. So you need to be very careful. You need to learn. You need to know how many samples do I have? What is the dimensionality of these samples? How can I sort of like pre-process or clean these samples so that it makes it easier for the model to learn from this data? And sort of all of these 3 questions sort of directly influence what learning algorithm you would be using. So if you have very few samples, you cannot go for a huge deep learning model. If the dimensions are very high, can a very traditional or simple algorithm learn this data? Probably not. What can I do with this high dimensional data? Can I reduce the dimensions? Can I get rid of some unnecessary features that this data already has? So this sort of like influences what algorithm should I be using for this use case. You need to use an algorithm that binds well with this data. So sort of there are different learning tasks, and there are different learning tasks that different sort of algorithms can do well. And so you wouldn't want to use, for an example, a model that in the past has worked really well for vision data on textual data. This is like a very extreme example, but so you properly have, I'm just like, I don't know if you guys would understand this, but just like throwing some terms around. But popularly, you have convolutional neural networks, which work extremely well for vision models, but they do not work well at all for textual data, because text does not have that context between an image in itself. And similarly, but there are other examples such as transformers or like GPT. So these transformer models, they work well both for like, you can sort of very easily transform these models to work well for like image and text. So just like coming to the next point, so you should always take into account the amount of data you have, its dimensionality and pre-processing. Pre-processing is extremely important, especially in cases where you're dealing with text data. So when you have these large BERT-based models, you do not want to pre-process the data because they can work better with unprocessed data. So so you also want to look at what the computational cost of the approach is. And I know sort of now people are just like going wild with the biggest model with the largest amount of data, but that may not always be required for most use cases. And also, when you want to actually deploy your system in the real world, you want to be very careful about how much cost you're sort of incurring with every operation. And especially when you want to do this in sort of like a research setting, you also want to look at what is the past work that's been done in this area, and where can I bring a new innovation into this? What were the limitations of the past work? Is there some way in which these limitations can be solved? Yeah. So that was all from like my side. If anyone has any questions, I'll be happy to answer.